Connectedness is a fundamental property in graph theory that's particularly important to the topics that we're going to be discussing from here on. A lot of the theorems and properties we're going to be looking at only apply to connected graphs, or sometimes to connected components within a graph, and we'll talk more about what that means on the next slide. Now, connected in graph theory means essentially what you would expect it to mean based on the English meaning of the word. Two vertices are connected if and only if there's a walk from one vertex to the other, and a graph is connected if and only if every pair of vertices in the graph is connected. So look at the two graphs here. The left-hand graph is connected. If you pick any two vertices, there's always going to be a walk between them. The right-hand graph, on the other hand, isn't connected, since there isn't a path connecting vertex v1 to vertex v2, or to any other vertex, right? But we only need one vertex that's somehow isolated from one other vertex for the graph to be considered disconnected. So a graph that isn't connected can still be made up of so-called connected components. Now, this is almost what you would expect from the English meaning of the words. The first two parts of the definition here on the left are pretty self-explanatory. A connected component first has to be a subgraph of the original graph, and second, it has to be connected. The third requirement is maybe a little less obvious. What this part is saying is that for a component to be a connected component, for a subgraph to be a connected component, it has to be, in a sense, maximal. That is, there can't be a larger connected component that contains it. All right, so to see this, take a look at the graph here on the right. This graph has two connected components. The upper left section made up of vertices 1 through 4 and their associated edges, and the lower right component made up of vertices 5, 6, and 7 and their associated edges. Now, take a look at this subgraph. It meets requirements 1 and 2. It is a subgraph of the original graph, and it is connected. However, it isn't a connected component, since it doesn't meet requirement 3. And it doesn't meet that one because it's contained in this connected subgraph, which is bigger in the sense that it has vertices and edges that the original one doesn't. So I've got some properties here of connected graphs. The proofs of these is relatively straightforward. So if you're following along on the website, I'm going to leave these to cover there, right? So if you go and check that out, these will be in the exercises area, and the solutions will be there as well if you want to look through them. I do want to make a special point about item A here, since at first glance it may seem a little obvious. It may seem that that's just the definition, right? But if you look carefully, the definition says every pair of vertices must be connected by a walk. Where item A here takes it a little further and says they actually have to be connected by a path. So you're going to have to look up the definitions there, right, and be very specific about what you're trying to show. So at this point, we've covered a whole lot of definitions, seen some examples, seen some properties, and that lemma from the previous slide. At this point, we finally have all the tools in our toolbox that we need to circle back around to that question we talked about in the very first lecture in the series, where we talked about the bridges of Königsberg. So in the next lecture, we're going to define something called an Eulerian circuit, or an Euler circuit, and see how we can use those to finally come up with an answer to those questions. So if you like this video, this lecture, please click on the like button below. And there's also some links here that will take you to that next lecture and back to the previous lecture if you'd like to review those definitions first.